Good afternoon, class. We are looking at Chapter 2, Limits, Section 2.4, Limits, Algebraic Methods. So we covered limits of sequences, limits of functions at infinity, limits of functions at finite numbers, and now algebraic methods. Here's the synopsis of what we covered. Limits of functions at finite numbers, finding limits by numerical and graphical methods, definition, and we read it in this manner: the limit of f of x as x approaches a equals L. So if you look at the following, the limit of a sub n as n approaches infinity equals L, that means we say that a sub n converges to L. However, if the limit of a sub n as n approaches infinity is infinity, or negative infinity, or does not exist, we say the sequence diverges. To find limits, simply plug in the value and observe. If we look at graphs as follows, and we are interested in this limit of f of x as x approaches a. If you look at the arrows, a along the x-axis from the left and right, along the curve from the bottom and top, along the y-axis from the bottom and top, we are approaching the this point which has the y coordinate L. The limit of f of x as x approaches a does exist, and it's equal to L for this, as well as this graph, all of it. What's the difference? The first one, f of a is also L. That means the function is continuous at x equals. In this case, f of a equals b, so the function is discontinuous at a, but functional value is given. In this case, f of a is not known at all. It's not given. It is discontinuous and f of a is missing. But in each case, regardless of what happens at a, the limit of f of x as x approaches a equals L, and that's the key. At a is the functional value. This is the limit. Horizontal asymptote of a curve y equals f of x has the equation y equals L if the limit of f of x as x approaches negative or positive infinity is L. And if the limit of f of x as x approaches a, or a from the left, or a from the right is either negative or positive infinity, then the equation x equals a represents the vertical asymptote. Reminding you of one-sided limit, a function has a limit as long as one-sided limits are identical, meaning limit of f of x as x approaches a from the left equals L, limit of f of x as x approaches a from the right is L, then the limit of f of x as x approaches a exists, and it equals a. Now, 2.4 limits, algebraic limits. We're going to look at limit laws. These are similar to limit laws for sequences. Let f of x and g of x be defined for all x over some open interval containing a. Assume L and M are real numbers such that limit of f of x as x approaches a is L, limit of g of x as x approaches a is M. Let C be a constant, some number. Then each of the following statements holds. Some law for limits. The limit of f of x plus g of x as x approaches a equals limit of f of x as x approaches a plus limit of g of x as x approaches a. In other words, L plus M. In short, the limit of the sum equals sum of the limits. Difference law for limits. The limit of the difference is the difference of the limits. Difference of the limits, L minus M. Constant multiple law. If you're taking the limit of c times f of x as x approaches a, you can take the c out, so c times L. Product law for limits. The limit of the product is the product of the limits, L times M. Quotient law for limits. The limit of the quotient is the quotient of the limits, L over M. As always, the denominator, in this case, M, cannot be 0. Power law. The limit of f of x to the power of n as x approaches a, you take the limit of f of x as x approaches a, and then you raise it to the power of n. In other words, L to the power of n for positive integers. Root law. The limit of the nth root of f of x as x approaches a is the nth root of the limit of f of x as x approaches a equals nth root of L for all L if n is odd. When n is odd, the index is odd, there is no restriction. But it has to be, L has to be non-negative if the index is even. And I'm going to quickly remind you of the reasoning behind that. Recall, if we have cube root of 8, the answer is 2. If we have cube root of negative 8, the answer is negative 2. No restrictions. But square root of 4 is 2, square root of minus 4, not a real number. It becomes 2i. That's why. Finally, k is a constant, some number. Limit of k as x approaches a equals k because it's independent of x. Also, reminding you of direct substitution property. A continuous function at a has the following limit value. Limit of f of x as x approaches a equals f of a. The functional value you basically plug in. All right, we're going to start with a warm-up example, and we're going to use the limit properties or limit laws for now. But ultimately, you can plug it. So limit of x squared minus 3x plus 7 as x approaches 4, you cut it into 3 pieces. The limit of x squared as x approaches 4, plus the limit of minus 3x as x approaches 4, plus the limit of 7 as x approaches 4. This one becomes limit of x as x approaches 4 to the power of 2. This one, negative 3, comes out. Now this is ready to be replaced by 4. This is ready to be replaced by 4. And this is a constant. It doesn't matter x approaches 4 or any other number because it's a constant. The answer is 7. And so 16 minus 12 is 4 plus 7 is 11. Or simply plug in. You could plug in. If it gives you an answer, you're done. If it doesn't give you an answer, it may be an indeterminate form. You have to figure out what you need to do. All right, we want to evaluate the following limits, and we are going to use the limit laws. And here's the graph. You can find them in the PowerPoints that are posted under the modules of Canvas. So we want to find the limit of f of x plus 5 g of x as x approaches negative 2. Bear in mind, f of x is the red one or the purple one, and g of x is the blue function. So we're going to use the limit laws and cut this into 2 pieces. Limit of f of x as x approaches minus 2, and 5 times limit of g of x as x approaches minus 2. So we're going to look at each one. So we're going to start with this one, limit of f of x as x approaches minus 2. So minus 2 is here. This is 0, this is negative 1, this is negative 2. And we want this one. If you want to find this, you're going to approach negative 2 from the left and right along the x-axis. And for the red curve, left and right, both of them takes us towards this hole. We never get there. And this hole has a y-coordinate positive 1. Now, the limit of g of x as x approaches minus 2. Again, minus 2, we are approaching it from the left and right. Here's the blue function. And approaching it from the left, we are going this way. From the right, we are going this way. And we are moving towards this point. And this point has a y coordinate -1. Therefore, this limit is this one, which is 1, plus 5 times this one, which is -5, adds up to -4. This is how you find the limit. The limit of f of x times g of x as x approaches 1. Again, with the limit laws, we're going to cut this into two pieces. The limit of the product is the product of the limits. And we're going to look at each piece. So the first piece is this one. So here's number 1. So we're going to approach it from the left and right. We go to the red curve f of x, and left and right, both of them from the left and right are moving us towards this point, which has a y coordinate +2. In other words, whether you approach it from the left or right makes no difference. You have the same answer, number 2. But what about the blue one? The blue one, the limit of g of x as x approaches 1 does not exist. Why is that? It has got to do with one-sided limits. So we are going to look at this as x approaches 1 from the left. Here's 1. From the left going this way, that means you are in this branch. And this one is taking us to this point, which has a y coordinate -2. Now going back to this one, we want to find the limit of g of x as x approaches 1, this time from the right side. So the right side of 1 is here. We are in this branch now. It's moving us, taking us towards this hole, which has a y coordinate -1. And obviously, these two are not the same. The limit of g of x as x approaches 1 from the left and right are different. Limit of g of x as x approaches 1 does not exist. Therefore, this limit doesn't exist. In fact, any operation, even the limit of sum, for example, does not exist. And we're done with that. But I want to look at a second method, and looking at this one, taking the limit as x approaches 1 from the left and then from the right. So I'm going to go to this one from the left. This one, left and right is the same, everybody is 2, but this one from the left is -2. So the product of 2 and -2 is the answer here. Limit of f of x times g of x as x approaches 1 from the left, and it's negative. Now, for the right side, the limit of f of x times g of x as x approaches 1 from the right, I go back to this one. Again, from the right or left makes no difference. This is 2, but this one from the right is -1. So 2 times -1, -2 is different than -4. So either method is fine. I just want to make sure you are comfortable with that. Finally, it's important to look at a couple of points. For example, f of -2. So you look at -2 along the x-axis, and for the red function, you look for a solid point. This is the point which has the y coordinate +2. G of 1, you're looking at the blue function, okay? And you locate number 1 along the x-axis, and because you want g of 1, the functional value, you look for a solid point, which is this one, and this solid point has a y coordinate -2. This, I just want to make sure we can do the reading as far as the graph is concerned. Okay, everybody? We're going to continue. We're going to look at the limit of absolute value of x over x as x approaches 0. It does not exist. Why is that? It has got to do with one-sided limits. So let me go over a couple of things. First and foremost, let's remember what's absolute value of x by definition is distance from 0. Therefore, absolute value of x is x if x is greater than or equal to 0, and it becomes negative x if x is less than 0. So that's the first thing we want to make sure everybody is comfortable with. Now, for this one, if we want to look at this function, f of x is absolute value of x over x, then we put x over x if x is positive, and we put minus x over x if it's negative. Bear in mind, over here we have the equality. But over here or here, we can't have equality because the denominator has x. Of course, x over x is 1, minus x over x is negative 1. And so f of x is either 1, that means y equals 1, a horizontal line, or y equals negative 1, a horizontal line. This one starts from 0 and goes to the right. This one starts from 0 and goes to the left. And so that's the graph according to this. So y or f of x equals absolute value of x over x. This is the line y equals 1, but it's a half line and the endpoint is not included. Again, we don't have the equality. This one is the line y equals negative 1. This is a half line and this endpoint is not included either. Now, we want to look at the limit. We're going to look at the one-sided limit. Therefore, the limit of absolute value of x as x approaches 0 from the left. We want to go this way. So we are in this branch and it's going towards the y coordinate negative 1. We want to look at the same thing, but this time as x approaches 0 from the right. So we are on the right side of 0, which puts us in this branch. It's moving towards this point, which has a y coordinate 1. The one-sided limits are different. Therefore, the limit of absolute value of x over x as x approaches 0 does not exist. All right, we want to find the following limits. The first one is the limit of the square root of 2x squared plus 1 over 3x minus 2 as x approaches 2. So simply put, you plug in 2. I hope you see that if you put 2 times 2 squared plus 1 over 3 times 2 minus 2, and the numerator becomes 9, the denominator becomes 4, comes out as 3 halves, and you're done. In other words, you plug in, it works out. Part B, the limit of 1 over 4 plus 1 over x plus 4 as x approaches minus 4. So we are dealing with a complex fraction. If we plug in negative 4, I hope you see the denominator is 0. This is 1/4 plus 1 over negative 4. That is also 0. So you get 0 over 0. So you have a complex fraction. When you plug in, you get 0 over 0. 0 over 0 is indeterminate, which means more work. And the algebraic technique is LCD. You have two fractions at top. The LCD is for x. You are going to multiply and divide by 4x because this expression must be 1. Otherwise, you can't just multiply the top by. Now, bear in mind, when we have 0 over 0, it is the 0 in the denominator that is bad we want to get rid of. So if you plug in negative 4, this becomes 0. You never distribute, rather you write this as a product. But this one, you distribute and you simplify. And when you do that, 4x times 1/4 is x. 4x times 1 over x is 4. I'm assuming no one has any problem with elementary algebra of complex fractions. These two cancel each other. We get the limit as x approaches -4 of 1 over 4x. And if you plug in, you get 1 over -16, which is -1 over 16. Normally, the negative sign, you put it either at top or in front of a fraction bar. The limit of x squared minus 25 over x squared minus 5x as x approaches 5. If you plug in, you get 0 over 0. And as always, it's the 0 in the denominator, which is a problem. So you have a rational expression. So the technique involved is factoring. Now, also, x is approaching 5, which results in 0. Therefore, you expect a factor of x minus 5. If x is approaching 8, you expect a factor of x minus 8. If x is approaching -1, you would expect a factor of x plus 1. I'm telling you this because it will help you factor. In case you have a difficult time with factoring, needless to say, 25 is 5 squared, and it uses a squared minus b squared equals a plus b times a minus b. So let's factor this. So the numerator, so limit as x approaches 5 up. The numerator is x plus 5x minus 5. The denominator is x times x minus 5. And let me erase my word. X minus 5 cancels out x minus 5. And the limit of x plus 5 over x as x approaches 5. Now, if we plug in, we get 10 in the numerator, 5 in the denominator, and the answer is 2. All right, if we plug in 4, we get 0 over 0. And since x is approaching 4, x is approaching 4, we should expect a factor of x minus 4. Also remember, for factoring, you want two numbers. The product is -4. The sum is -3. So obviously the top, you just take out the x, and the bottom becomes x minus 4 times x plus. So as expected, we have a factor of x minus 4. We drop that. And now when we plug in, we get 4 over 4. Now, the limit of square root of 1 plus h minus 1 over h as h approaches 0, the same thing. If you plug in, you get 0 over 0. Because we are dealing with a square root, the technique is to multiply by the conjugate of the numerator, and the conjugate of a minus b is a plus b, and their product is a squared minus b squared. So we're going to multiply by the conjugate of the numerator, which is square root of 1 plus h. You change this one to a plus sign. You're going to multiply and divide because this expression must be 1. Now remember, h is approaching 0, and it's the 0 in the denominator which is a problem. So you never ever distribute, you just multiply them in this fashion. And when you multiply these two, the numerator changes to square root of 1 plus h quantity squared minus 1 quantity squared. So square root of 1 plus h quantity squared comes out. 1 and negative 1 cancel each other. H and h cancel each other. And now if I plug in 0, square root of 1 is 1, with 1 is 2, 1/2 is the final answer. For part C of the same example, works out the same. You plug in -4, it results in 0, 0. The numerator involves a square root. The technique is to multiply by its conjugate. We have to multiply and divide. When we do that, remember, x is approaching -4, so x plus 4 is a problem. You keep it as a product. So you don't do anything to the denominator. You keep it as a product. I'm going to simplify the numerator. So a minus ba plus b is the square root of x squared pi plus 9 quantity squared minus 5 squared. This comes out as x squared plus 9. This becomes 25. These two numbers add up to -60. So look at the denominator. We are not touching it. We keep it as a product because we are hoping to get rid of x plus 4. The numerator is x squared minus 4 squared, so it's x minus 4x plus 4. X plus 4 drops. And now we are going to plug in. You plug in -4 for the top, you put the -4 for the bottom. The -4, when you square it, becomes positive 16. So 16 and 9, 25. So the numerator becomes -8. The denominator, this comes out as 5, becomes 10, simplifies to -4 over 5 as the final answer. So an indeterminate form of 0 over 0 can turn into any result.